These are not necessarily same percentage. They can have higher or lower percentages. And those are just the ones that are in here are actually higher than these two. So like different ones that were ours, so just say these are all the same energy level. They're generative. These 6, these two would generate, yes. They can generate the same energy level. But these ones are higher than these two.
Well, they have the same energy level that are two. Okay, so like these 6 are higher.
You just
To each other.
To each other.
Yeah.
I know.
Nice.
This is
Are higher
me.
than these.
Yeah.
Only by a little. But then, they're all higher than these two.
Like,
You're so nice.
yours, one S is 2. And then it's like around the same.
Yeah, they're the same.
Feels like voice drawing.
That's just like, forget about the smaller energy gaps, with the big energy gap. This one. The energy difference between these and these is big.
You're gonna say something to me? Nutella?
These. Well,
Nutella,
I'm taking the I'm doing good for the bacteria, right?
not going to this level. I don't have to really think about
It's up in the house.
I've no care.
I feel like Timo is missing.
I can't believe
Sandra is over there.
And I can't draw.
Cody?
She's already taken chemistry, she doesn't need to do it.
That's awesome. Good for her.
Just give me a
Timo also probably. Yeah, Timo and Cody also, both of them already did the course.
They don't have to do chemistry, they're just doing bio.
Yeah, and the practical, not and the practical.
Wow.
Because he did and he asked to transfer.
All right, let's continue.
He did a
So Lewis structures are represented. We can represent molecules with Lewis structures. And I can tell you something. This is how they're always represented, right? If you read any chemical publication, you will always see these. These are some Lewis structures of some important molecules, and on the right we have so-called ball and stick models. Okay. These are representations of what these things look like in 3 dimensions. Ammonia, this is formaldehyde used to preserve dead things, tissues and so on. Water, methane, SO2 and carbon dioxide. So the point is, the take-home message is we can have double and triple bonds. The octet rule we're trying to fulfill. We have bonding pairs and we have lone pairs. Okay. Now again, this is just something that I include. This is sort of a flow diagram which you can look at of a guide as to how to draw Lewis structures, okay, with some general rules. As I said, follow an intuitive approach to doing this. In other words, I put the electrons, I put the atoms down on paper with the dots and I start marrying them together until I get something that obeys the octet rule, right? That's the way I do it. Some other people like to do it in a sort of a more, let's say, methodical way, using a flow diagram, sort of a logic tree, if you will. I've never done it like that, and I've also never taught it like that. So I think it's more intuitive to just put it down and start marrying things together, because it means that you understand the chemistry, not just following some sort of a routine. So maybe we should just do one more example. Let's suppose I want to draw the Lewis structure of CO3 2-. Now that's the carbonate ion. Now the thing is charged, it's got a 2- charge. So let's not worry about that for the moment. Let me just show you how one would do this. Which atom is going to go in the center, carbon or oxygen? Right, carbon, because it's the most electropositive. So just put them down, sort of distribute them around, and put in the valence electrons. Carbon has 4 valence electrons. Let's draw it like this. Right, and oxygen, each oxygen is how many? 6. Now, you can use dots, you can also use crosses to help you. That's why it's called a Lewis dots structure, but you can also use crosses to help you distinguish things. So let's denote the valence electrons for oxygen with crosses. Now, the thing has got a charge of 2 minus. What am I going to do with that? I add 2 electrons where? To the oxygens. Why? Because they're the most electronegative. So if I put in 2 electrons, the most electronegative elements is going to take them. So let's put one here, and let's put one here. Now what do? Marry things. These 2 are going to get married, and these are going to get married. So what I'm going to get is something that looks like this. If I just draw this a little bit clearer, this is what we're going to get. This is perfectly acceptable as a Lewis structure, if you want to draw it like this. And I have these 2 here, and that is the Lewis structure, which I can in fact represent, if I want to, like this. So I'm throwing in a lot of different notations here. Don't get confused. But there is a problem here, isn't there? What is the problem? The carbon only has 6 electrons, so it's actually not a perfectly acceptable Lewis structure. So what do I have to do?
Make one O a double bond.
Correct. I have to take one of these lone pairs. So this guy is now electron deficient. Okay, this guy's only got 6 electrons. Right? These are just 2 representations. The lines here represent bonding lone pairs, by the way. You can represent it like that for all sorts of different representations. So what I'm going to do is I'm going to take, for example, one of these lone pairs and make it into a bonding pair. And then I'm going to get this. That would be the Lewis structure for a carbonate. So I overcome this problem of the electron deficiency on the carbon by just taking a lone pair. I could also have taken this lone pair or this lone pair. It doesn't really matter. I'm going to get to that in a minute. It's this notion of resonance. But this is then the Lewis structure of the carbonate ion. Okay, you see there's only two lone pairs here. Okay, so that's sort of what I mean by doing it in an intuitive way. Put everything down on paper and play with it until you end up with something that is reasonable. And you can check if it's reasonable by checking that each of the atoms has 8 electrons around it. They do. 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. They all have 8. Everyone's happy. Okay? So, I want to now talk about different types of bonds. We have different bond polarities. So if I marry 2 atoms together, depending on the electronegativity, a concept that you've encountered in the last task, hopefully, depending on the difference in electronegativity, you're going to have different types of bonds. Now there's 3 types. The first type is a simple classical covalent bond, where the difference in the electronegativity between the 2 atoms is very low. That means that those 2 electrons that form that bond between those 2 atoms are going to be equally shared between the 2 partners. That's a classical covalent bond. If the difference in the electronegativity increases, then what's going to happen is that bond is going to be more polarized towards the more electronegative atom. Okay? We would call that a polar covalent bond. And in an extreme case, for example, sodium chloride, where the difference in electronegativity, say, between sodium and chlorine is more than approximately 1.7, that it would become so polarized that there would be complete charge transfer from the one atom to the other, and it would actually be a so-called ionic bond. So let's just write those terms down, because they're important. Covalence ionic. Okay? So those are the three types of bonds that we have between two atoms. Now what I've represented here is basically, this is an electron density map of ammonia, NH3, okay? And what you can actually see here is that this molecule is polar, right? It's overall polar. We're going to get stuck into polarity later on. But what I actually want you to focus on is just the fact that you look at the difference in the electronegativities between nitrogen and hydrogen. You'll see that you have a positive and a negative extreme. And if you look here at this ball here, so this is a model of where the electrons are sitting in this molecule, an electron density map. You'll see that it's blue by the hydrogens and red at the nitrogen. Why is that? Nitrogen is much more electronegative than hydrogen. It's an example of a polar covalent bond. The bond between the nitrogen and the hydrogen is polar. What about chlorine, Cl2? Would that be a polar covalent bond? What sort of a bond would there be between two chlorine atoms?
Equivalent, because they have the same electronegativity.
Correct, correct. They're electronegative atoms, but the difference in electronegativity is 0. What about hydrogen chloride, HCl? Not ionic, but polar covalent. Okay, so, and what about cesium chloride? That's ionic, right? There's a very big difference in electronegativities. And how do we know these differences? We know from the trends in the periodic table that if you marry an element on the left with an element on the right, there's going to probably be a very big difference in the electronegativity, and it's going to result in an ionic bond, okay? But what I would like to say at this point, and this is an important point, Mother Nature doesn't like to be categorized into boxes, okay? And it turns out that every bond has a degree of covalency, a degree of a bit of ionic nature in it, and so on, right? That's the reality. But as scientists, we like to put things in boxes so we can understand it. So that's why we have these 3 boxes here. But most bonds have a bit of everything, okay? So if you take, for example, hydrogen chloride, and you do a bond analysis of the bonding interaction between hydrogen and chlorine, you will see that there's actually quite a lot of ionic character in the bond. But overall, we call it a polar covalent bond, right? So it's sort of a combination of all these things.
Is
Yes.
there like specific difference in electronegativity that's not on
The cutoff line is, well, depending on what textbook you read, the cutoff is typically 1.7, right? Above 1.7, it would be classified as ionic. Okay. Here we have some more of these beautiful electron density maps showing some highly polar covalent bonds, some of them. Hydrogen, you can see everything is the same color, so there's no difference there. That's a classical covalent bond. Look at lithium hydride, right? This is an extremely polar covalent bond. The lithium being extremely blue. Remember, blue is the positive extreme and red is the negative extreme in terms of electronegativity. That would be how the electrons would be distributed in that molecule. And so on. Hydrogen fluoride, again, you have a negative and a positive extreme. The fluorine being the most electronegative here. And this is an example of, this is chloromethane, an organic compound. And this is methyl lithium. This is a very interesting reagent which is used in synthetic chemistry. This guy here, this bond is extremely polar between the lithium atom and the CH3 group, the carbon. You can see there it's represented from these electron density representations. Methyl lithium from the Department of Useless Information, it burns on contact with air. In other words, if you take this guy out as a solid and expose it to air, it will burst into flames spontaneously. It's very reactive, and it's reactive because of this extremely polar bond.
And what is it used for?
It's used to put methyl groups onto metals, for example. So if you take my course in organometallic chemistry, this is a reagent that's used. It's a beautiful reagent to cleanly put a methyl group onto a transition metal and replace chlorines with methyl groups to make metal alkyl complexes. Right, so this is what I've just basically said. Polar covalent bonds, difference in electronegativity, if there's no difference or a small difference, it's a 0.2, you'd still call that a covalent bond. As the difference gets bigger, it becomes more and more covalent until you get complete charge separation in the case of something like sodium chloride. This is the electronegativity table. So here we have the electronegativity according to the Pauling scale. So there's different scales for electronegativity, right? You have also something called a Mulliken scale, but the Pauling scale is given here. This is the one that's traditionally used. You can see fluorine has an electronegativity of 4. It's very high. And you can basically see that this is in line with the trends that we observe, that the electronegativity increases from left to right and decreases from top to bottom, all that stuff that we hopefully will be discussing today in the tutorial.
Right. And the metal gases are known there because they're 0, because they're fine?
They're not 0, but the electronegativity is quite low.
Okay.
Now again, Mother Nature doesn't like to be put into boxes, right? These are 3 distinct categories: non-polar covalent, or just covalent, polar covalent, and ionic, like a full charge separation. So we go from one extreme to the other, and I'll notice that it's a continuum, like I just said, and that you have categories in between. Like you could have something on this side here. This would probably be something like that lithium methyl that I just showed you, the methyl lithium. So there's examples of compounds that fall in between these extremes, but of course as scientists we like to categorize things. So these are sort of the 3 categories, or some people would say categories, into which we organize our lives. Okay, there you see it. This is sort of 1.5. This is the approximate difference. This is anything greater than that would result in what we would call an ionic bond. Okay, but that's again just it's a name. Okay, and bonding situations. As a scientist, I can assure you that explaining the bonding interaction between 2 atoms is very difficult. Okay, what we do here is very simple, but the more chemistry you study, the more complicated and murky things get, and you start having to talk about 20% ionic and 80% covalent character and stuff like that. It becomes complicated. But this is, for the purposes of a first-year course, I think already doing pretty well. Okay. Here we have more examples, just to really pin this down. This is what I was talking about, this percent ionic character, the sliding scale, the way that you should think about things being a continuum. You can see that the ionic character increases. If we get to lithium fluoride, for example, that's an extremely big difference between the lithium and the fluorine in terms of electronegativity. But its percent ionic character is, let's say, 97%. That means there's still 3% something else. And that 3% is probably covalent. So there is a degree of covalency, believe it or not, even in that bond. And if we go down to, for example, these guys down here, IBR, there's a very little difference in the electronegativity between iodine and bromine, but you can see that there is nevertheless a degree of ionic character in that bond. But I think this is just to show you, again, that this is a continuum. Yes?
But why did we create it like those 3 categories, and why would you just not only talk about difference between electronegativity?
Well, I mean, I think people created these 3 categories because people want to organize concepts and ideas, right? And chemistry is a science, and we want to, in order to make sense of the world around us, we sometimes create categories into which we can put things so we can understand them. I mean, the reality, it's not a bad approximation, but the reality is more complex, and that's what I'm trying to say to you. The idea of, well, this is an ionic bond, this is a covalent bond, it's not really correct, but it's a way of organizing the world around us. Chemistry is about models and trying to use simplistic models to understand bonding.
Do they have like specific
Ranges,
specificities, specificities or qualities?
Well,
because they're characterized like, since they have different names, like what is the difference between a polar covalent bound and an ionic bound, except the difference in electronegativity? I mean, do they exhibit specific properties?
Well, certainly. I mean, for example, they have different physical properties. There's no doubt about that. I mean, if you take sodium chloride and dissolve it in water, it dissolves because you have this charge separation. If it's polar covalent, that won't happen. So yes, there are physical properties that are tied to this. But you know, the sort of the hand waving thing is that if the difference in electronegativity is 1.5 or higher, it's ionic. Anyway, I mean, this is just a note on that, the different types of bonding. Let's now move on to looking at some more issues with drawing Lewis structures, formal charge resonance, and exceptions to the octet. That should be a T, octet rule. Now, formal charge is basically something that's very important. We can assign formal charges once we've drawn Lewis structures. So I'm now coming back to Lewis structures, We can assign formal charges to atoms in a Lewis structure. And basically, this is related to what I've just said. If a bond is not totally perfectly symmetrical, and the electrons are spending more time on one atom than the other, it's going to result in a sort of a charge distribution, an asymmetrical charge distribution, which we can kind of capture in a concept called formal charge. Now, formal charge is not something that you can measure, but it's something that you can calculate. And the formal charge is defined in a Lewis structure per atom. So you calculate the formal charge for each atom in a Lewis structure, okay, as you can see here. So the way that we calculate formal charge is we take the number of valence electrons minus the number of lone pair electrons minus half the number of bonding pair electrons. Let's do an example of calculating formal charge. Let's take nitrogen.